See, good afternoon. Actually, in this lecture, I am going to explain you this 8254, which is programmable interval timer, the modes of operation of this IC. I hope you already watched the videos. Now, see, whenever we want to use 8254, we have to initialize 8254. For initialization of 8254, we have to enter a control word in the control word register. 8254 bit. So with these two bits, we can select a particular counter. That means if we enter 00 out here, then it will select counter 0. If it is this is 0 and this is 1, then it will select counter 1. For 10, it will select counter 2, and for 11, it will select control word register. Now, here it is written RL0, RL1. So it is for read load the word in the counter. Now we know that the size of all three counter, that is counter 0, counter 1 and counter 2 is 16-bit. But we can use them as 16-bit counter or we can use them as 8-bit counter. So if we want to use it as 8-bit counter, then we have to enter 8-bit count. So if we want to enter 8-bit count, we can enter count at this position, that means at least significant byte position, or we can enter at most significant byte position. Okay. And for that, there is a choice. Like if it is 0, 1, then we can read or load least significant byte only. That means if we are connecting 8086 to 8254, 8086 can read the counter or it can write count into the counter. So that's why if 8086 wants to read, it is a read operation, and if 8086 is writing into the counter, it is a load operation. So that's why it is written read slash, here it is written read slash load. So if we want to use this portion of the counter for reading or loading the count, then the combination byte should be 0, 1. If we want to use this, or if 8086 wants to read most significant byte of the counter, or if 8086 wants to write into this position, then the combination of these two bits should be 1, 0. But if we want to use full 16-bit counter, that means 8086 wants to write all 16-bit counter. That means both bytes, LSB and MSB. 16-bit means 2 bytes. Or 8086 wants to read both the bytes. In that case, we have to enter here 1, 1 so that processor will first read this byte and then read this byte, or it will first write. If it is a write operation, it will write this byte and then it will write this byte. Then what is for 0, 0? If it is 0, 0, it is written that it is a read back command. So what is meaning of read back command? The meaning is, as I said, microprocessor can read the counter. Whatever count is stored in the counter, microprocessor can read. But microprocessor can keep reading the count even if the counting is in process. Okay. So let me again make you understand. Unless you know the block diagram, you will not understand this. I hope you already watched the block diagram of 8254. Huh? Based on that, I am explaining this. So during the counting, if 8086 wants to read the counter, then this should be 0, 0, which is known as read back command. It is also known as counter latch operation. 8254 operates in 6 different modes, that is from mode 0 to mode 5. If we want to use 8254 in mode 0, these 3 bits, 1, 2, 3, M0, M1 and M2 should be 0, 0, 0. If we want to use 8254 in mode 1, then this should be 0, 0, 1 and so on. For mode 2, this is don't care and this is 1 and this is 0. Don't care means you can put here 0 or 1. Preferably, we will always keep 0 for don't care. For mode 4, it should be 1, 0, 0, and for mode 5, it should be 1, 0, 1. Then 8254 can be used for counting of binary counting or BCD counting, binary counting or binary decimal counting. So if we want to use 8254 as a binary counter, in that case, here the bit should be 0. And if you want to use it for BCD counting, then this bit should be 1. Now let's take one example. How to write control word. What is written? Write control word for using counter 0. That means we want to use for our application, we want to use counter 0. For selecting counter 0, what should be the bits out here? SC0 and SC1. S stands for select, C stands for counter. Select counter is a bit name. So both should be 0, 0. Then what is written? Read load LSB. This indicates that we want to use the counter, that means counter 0, as a 8-bit counter. We want to use it as a 8-bit counter, and for reading or loading, we want to use this portion of 16-bit counter. That means counter 0, we want to use list significant byte portion, and for that, who decides for read load LSB, these 2 bits should be 0, 1, RL1, read load 1, read load 0. This you can see here, this it should be 0, 1. So here we have to enter 0, 1. Now suppose we want to use this 8254 in mode 0. For mode 0, this mode select bit should be 0, 0, 0. So let us enter here 0, 0, 0. And suppose we want to use 8254 as a binary counter. For binary counter, this bit should be 0. So what we have to enter in the control word register, if we want to initialize and use 8254 according to this requirement, it should be 0, 0, 0, 1 and 0, 0, 0, 0. This is binary numbers. Now let's convert it into hex number. When we convert it into hex number, 0001 is 1, binary 10, but it is hexadecimal 10. So we have to enter this 10 in the control word register. Okay, now let's learn modes. How many modes are there? There are 6 modes, that is from mode 0 to mode 5. Let's start with mode 0. Okay. Mode 0, the name of mode 0 is interrupt on terminal count. Okay. Now let's see what happens in mode 0. So what is written? Write control word for using counter 1. Now we want to use counter 1. We can use any counter for any mode. Choice is ours. So here it is written, write control word for using counter 1, read load LSB, mode 0 and binary counter. Mode 0 because we are studying mode 0. And as a binary counter. So for that, our control word become, as we have seen earlier also, there we used counter 0. Now here we want to use counter 1. So these bits are different. That is select counter becomes 0, 1. So what is our control word for these requirements? So our control word is 50. It is in hex. 0101 is 5 and 0000 is 0. So this is in hexadecimal. Now you should know how to write the control word. Most of the time these kind of questions are asked in the compulsory question in question number 1 for 5 marks for writing the control word. So this concept, whatever is written here and whatever is written here is very, very important. Now let us assume that we want to use a counter for counting 4 clock cycles. 4 clock cycles. Now, how will be the clock cycles? Now, see. Now, you have already seen the block diagram of 8254. So, this is block diagram of 8254. At each counter, there are 2 inputs, that is clock and gate. And there is one output, that is out 0. Now, gate is used for triggering the counters. That means to switch on the counter. At clock input, we apply a square wave, that is clock input, and at out, we will get different shapes of waveforms. Remember, at clock input, we apply clock signal square wave. At gate, we have to apply particular signal to switch that counter on. And at out, we will get different shapes of waveform based on in which mode we are using 8254. So let's see this diagram. So this waveform, this is a square wave which is applied at the clock. Okay. We assume that we are using 8254 for counting 4 clock cycles. 4 clock cycles. Okay. You know what is 1 clock cycle. This is 1 clock cycle. This is second and so on. So first we have to enter control word. Suppose somewhere here we have entered control word and somewhere here we have entered count in the counter. Which counter? We are using counter 1. So it will enter into counter 1. Now for mode 0, gate is continuously 1. So remember, for mode 0, gate is continuously at state 1. Initially out is 0. You can see initially out is low, it is 0. Now what happens as soon as we enter count? As soon as we enter count in the counter, we write count in the counter. After that, whatever is the falling edge. What is this? This is falling edge. See, this is rising edge of clock. This is rising edge of clock and this is falling edge of clock. So as soon as we write this word, as soon as we enter the word in the counter at the next falling edge of clock, the counter starts down counting. So it will down count like this is 1 clock cycle, this is second, third and fourth. So it will down count like 4, 3, 2, 1 and 0. And after 4 clock cycles, automatically out will make or it will switch from logic 0 to logic 1. So you can see here initially out was 0. As soon as we have written here this count, that is n is equals to 4. So it has at the next falling edge of clock, it has started down counting and after 4 clock cycle, it switched from logic 0 to logic 1. It changed its state from logic 0 to logic 1. So what actually this counter is doing? So here counter counted 4 clock cycle. You can see 1, 2, 3 and 4. So this is how in mode 0 your counter works. Now let's see how it takes place in the block diagram. Now for this, we know that what was our control word? Our control word was 50. And what was our count? Count was 4. Now let's see how it takes place in the diagram. Actually what happens inside the counter. Now here we have chose counter 1. Now our control word is 50 and count is 0, 4. Remember that microprocessors are always connected on the left hand side. Okay, and devices will be connected on the right hand side of interfacing IC. This is interfacing IC. We know that this A0 and A1 are used to select counters. Just now I told you, or in the block diagram of this, it is given that if it is 0, 0, it will select counter 0. For 0, 1, it selects counter 1. For 1, 0, it selects counter 2. And for 1, 1, it selects control word register. That means control word also selects counter and these address lines also selects counters. These address lines are connected to the address lines of 8086. Now read bar of 8086 is connected to the read bar of this 8254 and write bar is connected to write bar of this 8254. At a time, either read bar is 0 or write should be 1, A1 should be 0, and since we want to use this 8254, CS bar should be 0. So 8086 will transfer these signals to this 8254. So after that, what it does, it will select counter 1. Now next job is to write control word. So it will write control word into the control word register. Now see how control word flows. Control word will flow through this data bus. This data bus is connected to data bus of 8086. So this control word will flow through data bus buffer through this internal data bus to control word register like this. Now next job is to apply gate, that is, as I shown you in the previous diagram, in mode 0, gate should be at logic 1. So we have to apply logic 1 to this counter 1 to trigger this, to switch this counter on. After that, 8086 will write this count 04 into counter 1. Now what happens here? We have to apply this square wave to the clock 1. So what happens, as soon as this receives the first clock cycle, only one clock cycle. See, this is one clock cycle. As soon as it receives the first clock cycle, the count will decrement by 1, and earlier it was 4, now it will become 3. Now it will receive the control word. We are using counter 0, so it is 0, 0. Now read load LSB, so this is 0, 1. For mode 1, it is 0, 0, 1. And for binary counter, this is 0. So our control word is now 1, 2 in hexadecimal. This is hexadecimal number. Now, again, let's assume that the counter is again 4. Now, let's see how in mode 1 waveform changes. Now, again, this is your clock pulse. It is same square wave. Gate is initially 0. You can see here, gate is initially 0 and out is initially 1. In mode 1, gate is initially 0, out is initially 1. Somewhere here you have entered control word. What is control word? Control word is 12. So here you have entered control word in the control word register. Then somewhere here you have entered means 8086 entered. Count is equals to n is equals to 4 in counter 0. Why counter 0? Because we are using counter 0. So here it has entered count 0. Now what happens in mode 0? As soon as we enter the count, it starts counting. But in mode 1, it is not like that. Now here, when we send a pulse, here we have to apply pulse at the gate to trigger this counter 0. In mode 1, at the gate input, it is initially 0. Whenever we want that counter to start counting, we have to apply a pulse at the gate input. It is pulse, it is not continuous one. Remember, it is not at continuous logic 1, but it is pulse. As soon as we apply this pulse at the gate, then at next falling edge, here we have applied pulse at the gate. At the next falling edge, this is falling edge, down going. This is falling edge, next falling edge of clock. Here, the out will make transition from 1 to 0 and it will start counting 4 clock pulses. And after every clock pulse, the count will decrement by 1. So 3, 2, 1 and 0. And after 4 clock pulses, again it will make a transition from 0 to 1 and it will give you this shape at the out. So in mode 1, gate is not continuously 1, but it is initially 0. Then whenever we make it 1, after that it starts counting. Now what happens? Again here it is 0 and again if we give pulse at the gate. Other situation. Now here you can see this is right. Again here we have entered control word. Here we have entered count. This is a clock. Okay. The out is initially 1 and gate is initially 0. Somewhere here we have entered a pulse at gate. We have applied pulse at the gate. At the next falling edge, it will start counting. Now it has started counting 4 and it has decremented by 1. Now what happened? Again, if we apply gate pulse at the gate, what happens? Again here in between, before it completes the count like this, in between again if we apply a pulse at the gate, what happens? It will not consider this counting anymore, and again at the next falling edge it will start counting as a fresh counter. See, 4 like this, 1, 2, 3 and 4. So it is down counting 3, 2, 1 and 0, and after 4 clock pulses again it is 1. So this is only a situation. It is not necessary that you remember both the sets. You can only remember this set, but you should be aware of this. If someone asks you, what happens in between if again this gate goes high, so at the next falling edge, it will start counting again. So that is what you have to remember. Now what happens here? So here in mode 1, if we apply clock like this, and at the gate you have to apply, we have used counter 0 in mode 1, that's why I have shown it in counter 0. So here we have applied pulse at the gate, and out will show you this kind of waveform. So in every mode, the shape of out waveform is different. Now let's see next mode. Next mode is mode 2. The name of mode 2 is rate generator. Now let's see what happens in rate generator. Now again it is written write control word for counter 1, read load LSB mode 2 and binary counter. Let's see how it is. It is like this. What is control word? For selecting counter 1, again this is 0, 1. Then read load LSB, this is 0, 1. Mode is 2, so it is 0, 1, 0. And binary counter, so this is 0. So our control word is 54. This is hexadecimal, and again assume that our count is 4. Now let's see what happens in mode 2. Mode 2, again at the clock, suppose we have applied this waveform, gate is continuously 1. Suppose this is case 1. We are learning only this case. Okay. So gate is continuously 1, the way it was in mode 0. So out is initially at logic 1. As soon as we enter count, here we have to apply somewhere, here we have to apply control word and then say count. Okay. So as soon as we enter count in the counter at the next falling edge, this is rising edge, so it will not consider this, but this is falling edge. At the next falling edge, it will start down counting. But here the shape is different. How the shape is different? You can see here the count is 4. For 3 clock cycles, it is 1. And for last clock cycle, it is going 0 and again 1. So consider this. It is a rate generator. That means if count is n, then if count is n for n minus 1 clock cycle, for n minus 1 clock cycles, it is 1, and for last clock cycle, it is going 0. If count is 2, in between again you have written here another count, that is n is equals to 2. So what happens here? For 1, it will start counting here at the next falling edge. Here, this is a falling edge. And for 1 clock cycle, it is 1. And for 1 clock cycle, it is 0. And it will continue like this. So if count is 5, say, then for 4 clock cycle, it will be 1. And for 1 clock cycle, it is 0. And so on. If gate is continuously 1. But what happens if gate changes the status? Let's see here what happens if gate changes the status. Here gate is initially 0. So even if count is given, it will not start counting. It will start counting only when we apply here this logic 1. See here, when gate goes 1, after whatever is the falling edge, here it will start down counting. But condition is same. Count is equal to 4. So for 3 clock cycle, it is 1. And for 1 clock cycle, it is 0. Now here again, gate is going down. Gate is going 0. So it will stop counting in this area. Now again here, gate made a change. It changes its state from 0 to 1. So whatever is the falling edge after this, again it will start counting. For 3 clock cycle, it is 1. And for 1 clock cycle, it is 0. And it will continue this waveform as long as gate is 1. Remember, as long as gate is 1, it will continue giving the same shape of waveform. Okay, like this. Okay, gate should be 1. If gate make a transition from 1 to 0, it will stop counting. So it was about mode 2. We know that in every mode we get a different shape of waveform at the output of each counter, and that is the main purpose, because that waveforms are used and given to the appliances for generating the time delays. Okay, required time delays. For generating the required time delays, we apply that particular waveforms that we get at the out to different appliances and use them as a timer. And that's why 8254 is a timer IC, because it is used for generating time delays. Now let's see what is mode 3. Now again we will take the example, write control word for using counter 1, read load MSB. Now here for a change I have taken most significant byte position of that counter, mode 3 and binary counter. So what will be the control word for this? For selecting counter, since we are using counter 1, it is 0 1. Now for MSB it is 1 0 combination. Mode is mode 3. For mode 3 it is 0 1 1, and we are using it as a binary counter, so this is 0. So now our control word is 66. Again it is in hexadecimal, and like again assume that our count is 0 4. Now these are the waveforms. This is a clock waveform that we apply at the clock input. Now this is first set of waveform. Okay. Now let's assume that gate is continuously at logic 1. Now somewhere here we will write a control word, and then we will write here suppose a count in the counter. Initially out is at logic 1. You can see here out is at logic 1. Now what happens as soon as we write a count in the counter, you can see at the next falling edge, this is rising edge, so it will not consider this, but this is the next falling edge of clock. At next falling edge of clock, the counter starts down counting. Now our count is 4. So for 2 clock cycle it will be 1, and for 2 clock cycle it is 0. Again for 2 clock cycle it is 1, and again for 2 clock cycle it is 0. So that means what is it? Actually it is a square wave generator. What is this mode 3? Mode 3 is square wave generator. Only it is changing the frequency. So we are applying square wave at the clock. We are getting square wave at the out. But frequency is different. Here you can see the frequency is lesser than this. And the frequency of waveform, square waveform at the output depends on what is our count. If count is 4, for 2 clock pulse it is 1, and for 2 clock cycles it is 0. If count is 6, then for 3 cycles it will be 1, 3 cycles it is 0. If count is 100, then for 50 clock cycles it will be 1, and for 50 clock cycle it will be 0. This happens when our count is even number. Now what if our count is odd number? So if count is 5, then for 3 clock cycles it is 1, and for 2 clock cycle it is 0. Remember, if count is even, then it is 50-50, but count is odd, then for 3 it is 1, and for 2 it is 0. So if there are 7 clock pulses, 7, count is 7, then for 4 it will be 1, and for 3 it will be 0. Now here you can see different case wherein gate is initially 1, and when it goes 0 it stops counting. Here it stops counting, and then again whenever gate makes a transition from low to high, at the next falling edge it starts counting like this. For again 3 clock cycle it is 1, and for 2 clock cycle it is 0. Like see, you can see here. See, 2 it is 0, and for 3 clock cycles it is 1. So remember that for mode 3 gate should be 1. If you want a waveform at the out waveform. Remember that mode 3 is square wave generator, which is very important, and it is used in so many applications because mode 3 is simply changing the frequency of this clock. Now next is mode 4. The name of mode 4 is software triggered strobe. Now let's take an example. Write control word for using counter 0, read load LSB, mode 4 because we are studying mode 4, and as a binary counter. Now for this the control word is, we are selecting counter 0, so this is 0 0, again LSB, so this is 0 1. For mode 4 it is 1 0 0, and this is binary counter, so this is 0. So our control word is 1 8. This is 8 and this is 1. It is in hexadecimal. Now let again count is equals to 4. Now what happens in mode 4? Gate is initially 1. This is a clock that we have applied at the clock input. Now here we will enter some count, right? It is n is equals to 0 4 in the counter. Somewhere here we have to write control word in the control word register. Initially count is high. Now what happens for 4 clock cycle? As soon as we apply count, as soon as we write count in the counter at the next falling edge. So this is rising edge. After we apply count, this is next falling edge. At the next falling edge, it starts down counting. For 4 clock cycle, it is 1, and for 1 clock cycle, it is 0. Then what is difference in rate generator and mode 4? So in rate generator, if count is 4, for 3 clock cycle, it is 1, and for 1 clock cycle, it is 0. And in mode 4, that is software triggered strobe, if count is 4, for 4 clock cycle, it is 1, and for 1 clock cycle it is 0, and it will continue like this. Okay, now what happens? Now here you can see gate is 1, case 1. This is another case. Okay, now here gate is 1. So as soon as we enter a count here, at the next falling edge it starts counting, and you can see that here it has started counting 4. No, it was about to decrement the count here, and it was about to make it 3. But what happened in between? Gate made a transition from 1 to 0. Now since gate made a transition from 1 to 0, it has stopped counting, down counting. You can see here, since gate made a transition from 1 to 0, it has stopped down counting out here, and again here again it has gone up. It has made a transition from 0 to 1, and it was exactly at the falling edge of clock pulse, clock cycle. So it has started again down counting. So for 4 clock cycles it was 1, and for remaining, you cannot say remaining, for 1 clock cycle it has gone 0. So you will get this kind of waveform at the out if gate is continuously 1 in mode 4, which is software triggered strobe mode. Now what is next? Next is mode 5. The earlier was to software triggered strobe, and this is hardware triggered strobe. So in this written, initially the out is high, the counting is triggered by rising edge of the gate. When initial count is expired, the out becomes low from 1 clock pulse and then high again. Let's see how it happens. Now here it is written, write control word for using counter 0 for LSB, mode 5 and binary counter, and for this our control word is 1A. For counter 0 it is 0 0, for LSB 0 1, for mode 5 it is 1 0 1, and this is binary counter. So our control word is 1A. Now this is the waveform. What happens here? Gate is initially 0, out is initially 1. As soon as we apply gate, now here somewhere here you have entered a count also. Suppose somewhere here we have entered count. Okay. So as soon as gate make a transition from low to high, as soon as we trigger the gate, it is hardware strobe. As soon as we triggered the gate, at the next falling edge, it starts counting. So same thing, output is same. That is for 4 clock cycle it is 1, and for 1 clock cycle it is 0. Now what if the gate makes transitions like this? So initially you can see it was low, so there was no counting. As soon as it made a transition from 0 to 1, at the next falling edge it started down counting, that is 4, 3. And then again gate made a transition from 1 to 0. Here it is still counting. Here it is still counting. The earlier case, here it has stopped counting. What is difference in mode 4 and mode 5? In mode 4, which was a hardware triggered strobe, when gate goes low, it stopped counting and it was waiting for gate to go high. But here, even if gate made a transition from 1 to 0, it continued its counting. But what happened? Gate here it is 0, but when again it makes a transition from 0 to 1, it is not yet 0. This is 4, 3, 2, 1. And in between again gate made a transition from 0 to 1. So since it is a hardware triggered, hardware means you are triggering at the pin. The triggering is at pin. As soon as gate goes high, it will forget everything, whatever happened earlier, and again it will start recounting. Now here gate has gone low. I will show you. Now see here. Here again it has started down counting at the next falling edge, that is 4, 3, 2, and in between gate has gone low, made a transition from high to low, but it has still continued its counting like 4, 3, 2, 1 and 0, and for 1 clock cycle it is logic 0. That means for if count is 4, for 4 clock cycle it is 1, and for 1 clock cycle it is 0 if gate doesn't make transition in between. If gate doesn't make, if it makes a transition from low high to low, it will not stop counting, it will continue. But during counting, here you can say during counting, if gate makes a transition from low to high, then it will start recounting. And what happens in mode 4? It will stop counting. Whenever gate makes a transition from high to low, it will stop counting here itself. So there is very minute difference between mode 4 and mode 5. So all these modes are very, very important from exam point of view. Most of the time you will find questions asked on these modes. So if you have any